Hello and welcome to this lecture. Here we're going to talk about Chapter 1 from the textbook, The Physics of Everyday Phenomena. As you can see in the title, it is the subtitle, A Conceptual Introduction to Physics. So this textbook and these series of lectures covering all the chapters in the textbook are going to be light on the math, but not completely absent of the math. Okay, so we're going to have some arithmetic, a little bit of algebra, but we're not going to use a trigonometric approach. We're not going to do complicated calculus or anything like that. Okay, although of course modern physics and calculus are very connected ever since the Renaissance and kind of the beginning of the beginning of classical physics, which we call modern physics, which does begin in the 1600s. And actually the 1500s of the 16th century. And that's where our story begins, but our focus is not on the history, it's more on the concepts and applying those to our everyday lives and kind of building from there. But ultimately we are going to take a journey from those first physics concepts from thinkers such as Newton, which as I said tied in with the birth of calculus, and then carry that all the way up through modern physics and the last chapters of this textbook, where we're going to then be talking about turn of the 19th century, so beginning of the 20th century, when we're going to have the beginning of relativity and quantum mechanics, which are ideas we'll touch on at the very end of this class. Okay, and we this lecture series will cover all up until the last chapter. We actually will not be covering the last chapter. Usually there will be more than one lecture per chapter, but in this case, because chapter 1 is quite short, we're just going to have a single lecture here. All right, so let's go ahead and get to it. We are talking about a textbook here that is authored by Thomas Griffith, as well as Juliette Brosing, and it's the 10th edition, right? So a newer edition. Okay, so the spirit of inquiry is all about asking questions, the types of questions that are associated with children that want to know. And sometimes this idea is lost as we become adults, that we're no longer as driven by curiosity. And that is something that physics is supposedly addressing, right? That it is willing to and motivated to ask those fundamental questions and not call them a waste of time, not call them childish, but dig for those bigger truths. Because these everyday questions, of course, have some pretty complicated answers, especially if you continue to ask them, right? So, I mean, you might get somewhere like the Big Bang, right? I mean, there's a kind of a natural escalation of these ideas. Right? But going back to a rainbow, what's going on with these colors? Why that range of colors? Our eye can see those range of colors. That's actually the entire range of colors that our eyes are capable of seeing. All right, based on just the particular cells that we have. Not all animals can see the same colors, right? And then why, when there is a double rainbow, which if any of you've seen it, it's a rare phenomenon. I don't remember ever actually seeing one in person, but it's mentioned in all these physics textbooks and it's well documented. And it's the reverse. It's the reverse. So what's going on? Is it like a mirror image? Because mirror images are all about being reversed. We've seen that if we try to read our t-shirts in a mirror. So is that what's going on? Is this second rainbow? And like in this image here, we can see the red end of the rainbow in the primary rainbow, and the secondary rainbow having the red on the closer side, which means the opposite side, right? Is reversed. So is it a mirror image in a sense? But where's the mirror, right? The mirror must then be composed of the water droplets in the sky. And so that's the type of question that it ends up being answered by a subfield of physics called optics, and it's studying what light does as it behaves at this scale of visible light and the scale of water droplets. Okay, and scale, by the way, is a big part of the picture. But I'm getting ahead of myself, so let's take a look at the next slide. So one thing we'll talk about directly in this chapter that then we'll kind of take for granted as we move on is thinking about science in general. What is science? What is the scientific method? What is a scientific enterprise? What do scientists do? Right? Let's be clear about these definitions. These are things that we've been hearing presumably your whole life. If you haven't, then welcome to these ideas. But they still are ones that we generally need to clarify that at the college level in a course, I think we can talk about it in a clearer way than you would be presented in elementary school or high school. And also there's some very prevalent misconceptions about what science is, what's like how does science tie into our modern society in general. Okay, all right, so how do we explain things as scientists? Right? Maybe you don't think of yourself as a scientist, but you're going to kind of behave like one in this class as you go through and you do lab experiments. The idea is that you're going to do them best if you're going to adhere to thinking as a scientist as much as possible. So read previous ideas, all right? So definitely know what are the established ideas, why they work as much as you can, right? And as much background reading as possible. You then want to test these ideas against observations. So you want to have a testable idea. You can't have an idea that has no way to test it if you're actually going to follow through with this method, okay? When you are testing that theory, you want to have an explanation of what's going to happen. So this is your best guess. This is an informed guess, and that guess, that preliminary explanation, is called a hypothesis, okay? And the test, right, this testable idea then leads directly to a testable hypothesis. So in a sense, saying that your experiment has a hypothesis that can be tested is the same as saying that at the very, kind of like brainstorming stage of thinking, well, you're thinking of testable ideas, okay? You're thinking about what are the capabilities of the things you can test, right? With maybe whatever tools or equipment you have, and then even just fundamental capabilities, right? Because there's you can push up against kind of limits of what can be done, right? As you get to high energy or fundamental physics. Okay, but that's a story for another day. All right, but the idea, you have a testable hypothesis, which just means a testable idea. Okay, but continuing with these particular terms, right? Hypothesis, that's a very scientific method, scientist jargon type of term, but it is an educated guess, and it's the best term to describe this process. Okay, then you're going to have results, right? You can collect however much results, right? Whatever makes sense. There's a whole incredible subdivision of mathematics that is outside of physics or physical sciences in general, which is statistics, of course, and that gets into how what is going to make you confident about your result. And well, of course, it does sometimes comes down to some agreement between individuals of how much they trust the data and on what criteria. And that's what all that statistics is all about, is that the actual numerical values or numerical meaning of these of a range of values of error and so on. Okay, and do you continue to collect more data or not, right? Well, how much is enough? Then is this this idea, right, that then has gone on to something I'll mention in a second, become a theory, right? So this testable hypothesis that then has led to a lot of results, a huge body of data, or at least a large body of data, often huge, honestly, right? If you just think about the sheer kind of bits of it, computer storage and whatnot, everything's so big these days. So, but all that aside, is that this is just that it has to really stand up to be a theory, right? It has to continue to be tested. If within a scientific community, it has to be tested by multiple scientists. That's peer-reviewed, or the experiment has to be repeatable, right? And that's how we end up with a theory, whether it's in the physical sciences like pure physics, or some applied physics, or astrophysics, or chemistry, or biology, right? This is always going to be the same process. Okay. So this scientific method, which here we're calling the scientific enterprise, kind of a particular way that your textbook approaches it, right? The Griffith one that we're talking about here in this lecture series, is we got our cycle here where we can keep going, right? Because the results, one theory informs the next hypothesis in a sense, right? It's a continuing journey of exploration. There's no end to it, because there's always going to be something that can be redone, can be refined. Some either strange data will come up, whether it's just kind of spurious in the sense that it's just a result that's just some noise in the system, which is a kind of a term we use for just random results that inevitably happen, right? With a big enough set of results. Or does it actually mean that the theory needs some correction, some refinement? Did it not encompass certain conditions, because there's always going to be some simplification in every single experiment we do, in every single hypothesis and theory. There's always something that we assume, right? So if I'm going to do an experiment about gravity, I'm going to assume that the nucleus of the atoms that are creating the gravity are stable. Well, of course, because there's we have largely stable nuclei, right? But like that. What if? How much is that not the case? Because things are undergoing radioactive decay. That's a release of energy. How much does that affect gravity, right? So that's going to be some tiny effect to gravity due to the continual release of energy from like random nuclear processes, and it would, of course, depend on how nuclear active your atoms are that are generating the gravity. But and that, of course, I'm getting into the weeds here. But the idea is that you either correct for that tiny little detail that may or may not make a difference at all, right? To the level of your measurement capabilities, what's called sort of your significant figures, how accurate your measurements are. Or you may be actually, that's an important correction. And then you go back and collect more data and refine your theory, all right? Science refines its theories continually, okay? and models work great under certain conditions, simplified models, right? When we talk about gravity and understanding pendulums and things that we understand really well, right? Understanding, rotational motion and why bicycles can be balanced and all these sort of ideas, things we take for granted in everyday life. Well, those are all definitely, were hypotheses and tested and of course engineered in the case of bicycles, right? So the cycle, to explicitly say here what's going on, is we have observation or experiments that then go into some generalization. This is then going to lead to a hypothesis or a theory, right? Because some hypotheses don't make to a theory, right? Their best guess kind of ends there, maybe, or is outright rejected. It's like clearly not the case. Like somebody is really obviously refuting it, and so it's either set aside or just trashed. And then maybe so that could be the end of one hypothesis, not getting to a theory. But sometimes it doesn't quite. It's not a large enough body of data to call it a theory, and there's no absolute line between them. Okay, so those terms, if you think of them as hard and fast definitions, that a hypothesis is this, and it can only become a theory if, under this one particular guise, that's not true, right? There's definitely some gray area, but well-known theories like in biology, the theory of evolution, or the theory, the theory of gravity, right? Sometimes called the law of gravity, depending on kind of how you're coming at gravity, but things like that, Einstein's theory of general relativity or special relativity, those theories are incredibly well backed up. Like the sheer amount of human work and endeavor and publication that's got into them is mind-boggling over decades, right? And people dedicating their lives to it. So what you end up with is a very robust theory, right? But that's not the case for all. Some are much more particular and less well known, and not as backed up by as much data. Okay, and some remain hypotheses, as I mentioned. And that term law also is not a hard and fast difference from a theory. A law is just a very simple theory. In honesty, what separates the law, the term when I say that the law of gravity, that's because it's a direct observation that didn't really require any collection of data. It's just always true and never isn't true. And because the law of gravity is kind of the very simple case that two things attract, right? That matter attracts matter, right? Or in a very kind of like limited sense, if you're on the surface of Earth, things fall down, right? There's always going to be a force pointing downwards. That's the law of gravity, because it's an observation that's never refuted. Then the theory of gravity talks about the explanation, why the fact that it's the proportion, that this force between things is proportional to the product of the masses. There's this thing called the gravitational constant, which is 6.67 times 10 to the negative 11 Newton square meters over kilogram squared, one of the fundamental constants of the universe, a value that you will see in this class, right? But the point being is that that's the theory, the one with the constant and the more the actual formula, because it's not just a direct observation. It actually there had to be a hypothesis that was tested, right? And then you came up with that, that particular formula in this case, because a lot of times physics, fundamental physics, in the past at least, there's probably less opportunities for this today, would just lead to simple fundamental theories. So you have many cases of fundamental theories which were the result of hypothesis, right? So you just have the hypothesis becoming this, I say fundamental theory, I mean like a rather simple equation, right? Just a direct equation with some sort of constant that is going to represent the behavior between different criteria. Ohm's law in the case of circuits, the universal law of gravitation, Coulomb's law in the case of charges. These are laws that we're going to see, and they're just based on some simple relationships, from some proportionality and a constant, okay? Newton's second law of motion, same idea, okay? Now, we will repeat these ideas because that's actually one of the big ideas that you could kind of focus on and get out of a class like this, is what is physics, right? What is it trying to tell us, and how does it tie in with the big ideas, right? Like, the big ideas of what is human thought and human endeavor and so on. Okay, so how do scientific explanations, right? This thought question here, differ from other types of explanations, right? As I said, they got to be testable. That's what sets them apart. So if you have a non-testable observation, it could be it's like fiction, right? It could be belief, certainly, right? That would be on the non-testable side, and that's just it, right? Now, there's a huge amount of wiggle room between belief and science, right? Because you come in with some assumptions, right? Now, the assumptions that scientists come in with aren't based in like the same history as, say, like the assumptions that some religion comes in with, right? But they're still assumptions. They're still based on kind of like a cultural background. But when someone comes in with a religious idea, they acknowledge that it's not going to be testable, right? Because that's the whole approach that they built on, and especially the way that religion fits into the modern world. Now, sometimes these things do clash. There's misunderstandings, disagreements about what is belief and what is science. But there, you can come back to it if you agree with me as a rational thinker, that it comes down to whether something is testable or not. And that's all I'm saying. I'm not saying there's no room for belief in people's lives at all, right? But no judgment. But it's just that belief and science are different things. One is testable in the case of science, one is not in the case of beliefs. Okay? All right. So talking about the cycle. I'll skip over these ones. So the concept of a theory, right, this progression from a hypothesis, okay, it's often misunderstood, okay? When people talk about, when they use it in everyday language, it's, famously misused, okay? So a theory consists of a set of basic principles. These principles are often widely accepted. So I talked about this big body of evidence, lots of peers and agreement over, kind of generations of scientists, right? And a lot of willingness to criticize and dig into and question what came before, right? We don't accept it on blind faith at all. Scientists just fundamentally don't. It's the very kind of, again, to use that term, that very culture of the scientific community, okay? This global community, right? More or less. So theories are revised if new experiments reveal discrepancies, okay? Now they can be completely, thrown out. It can be kind of like, oh wow, this was not a very good theory, or just applied to one particular case because of this particular simplification, and it was a little misleading. That people would kind of stop using it, right? Sometimes, however, they kind of persist, and people still acknowledge, oh well, it does work in this case, but if it is misleading or it ends up kind of confusing people, then theories, they can kind of have some baggage, and they will literally be trashed, okay? There are kind of little smaller theories that have gone this way in recent decades, okay? I've seen it between older textbooks that I saw 10 years ago and the newest ones now, right? So probably more than 10 years difference between them. But point being is that a lot of times, though, a theory is revised in the sense that it applies to a particular situation. So like the classical theories we'll learn about, like the most famous three, I suppose, are Newton's laws of motion, all right? So they're called laws, right, because they're so fundamental, okay? So because they're such simple theories that required so little data to come up with that we call them laws, right? And the three laws of motion, now, they're great and they're completely reliable for things that don't move near the speed of light or aren't near really strong gravitational sources like neutron stars and black holes. And honestly, that's the thing. So because they don't work in those situations, and there's other theories that do. Now, those other theories also work on the everyday situations where things aren't moving fast or near hugely dense, sources of gravity. So the new theories, you could always use them, but it'd be overkill. It'd be like trying to blow up an anthill with a nuclear bomb, as the expression goes, right? It'd be like you don't need the incredibly complicated general theory of relativity to work with everyday motion, right? You could use it, but it would be completely unnecessary because Newton's laws of motion, give you a accuracy to whatever point you really realistically need it. All right, so that's an example where you have a theory that had to be revised, but most of the time can be still used to this day. Okay. Just has to be revised in particular situations. Ones that are very important to people who are trying to understand things like the Big Bang, understand black holes, right? What happens when you fall into a black hole? What really is it? What does it mean to be a hole in space and time? And those sort of questions. I mean, that's a great forefront of theoretical physics and maybe eventually more testable physics, right? Because there's an interesting side of physics which is coming up with all the ideas that maybe would be testable someday but aren't at all now, which does kind of cross the line into, is that still physics, right? Because you're acknowledging that those theories are not yet testable, right? So I wanted to mention here that we have a copy of the textbook, right? This is the e-text that you can access. And I bring it up because you can see in the slide, it mentions the everyday phenomenon, box 1.1. And if you read through this and just kind of, you might think, oh, it's a little childish, we got this cartoon, but if you just give it a moment of your time, it really just lets you just think about, kind of slowly going through it, what it means to troubleshoot something, right? To actually go through and take, go through that step of approaching a problem, and how that is not necessarily better than appealing to authority, which is a great way to solve a problem if you don't know how to solve it, right? But it is interesting to think about, is it something that maybe we don't do enough in our kind of modern skill set in terms of, actually thinking like a scientist, which is just thinking like somebody who is willing to troubleshoot and, fix things, to think about how things work, right? Ideas about, being willing to learn new skills, okay? Because that's very much what thinking like a scientist, thinking like a physicist is all about, okay? So there it is. We have our everyday, phenomenon, thinking about the spirit of inquiry. Okay, so I mentioned a couple times that there's a few branches of sciences. So life sciences, biology, health related. There's the social sciences, it's like sociology, anthropology, psychology, right? And then there's the physical sciences, which are pretty well delineated. So those are considered physics, chemistry, geology, and astronomy. Okay, you've got climatology in there, planetology, which would be a subsection of astronomy, cosmology, which is those people that study galaxies on the a population scale of mini galaxies and the evolution of the universe since the Big Bang. Those are called cosmologists because they study the cosmos, not to be mistaken with cosmologists. No, cosmologists is what I'm talking about. Cosmetologists, yeah, cosmetologists, right? Very similar words. Even I mix them up, and I'm probably not the best at mixing those words up because you'll notice sometimes I do say the wrong word. I do try to catch myself, okay? But physical sciences, okay? Now physics is the most fundamental of the physical sciences. It's where the name comes from. It is the biggest questions, the whys at the bottom level, the fundamental questions would all fall under the purview of physics, okay? Chemistry is specifically talking about a very prevalent but pretty particular case of how the electrons of atoms react with other electrons, right? So really that's it. It was a tiny, kind of subdivision of physics, not to sell chemistry short because it's so important for our everyday lives, right? We live in an environment where chemical processes are often more important and more accessible and more unique in their properties than physical processes, right? A lot of the, things like even nuclear fusion, we still don't have, access to on an industrial scale, right? When we have nuclear power, it's actually fission. And I'll talk about much later the difference between, in our chapter on nuclear physics, the difference between fusion and fission. Okay, but in this class, we are just going to focus on physics. There's, classes that are called physical science, where you go through all of them. And obviously, you can take individual classes on each. Okay, physics being the most fundamental, it's considered kind of a hard class, right? It's considered harder than geology or astronomy because there's bigger questions, And so there's a certain ambition to, listening to a lecture like this or going, or pursuing a physics class. And I hope that kind of motivates you and doesn't intimidate you. I don't mean it to at all. It's just, it is the, kind of the fundamental approach. Now, we don't, require obviously a ton of math here, so we skip over stuff, but we still ask big questions, okay, in this class. All right, so physics, what is it? Just to, kind of read through this slide here. We got the study of the basic nature of matter, so talking about atoms, talking about how light, which are composed of these particles called photons, which are massless, which is kind of interesting, a massless particle, how they interact with matter. Turns out both that massless particle, the photon, and particles of matter itself, like protons and neutrons, are all waves themselves. So they're actually particles and waves, which is called a duality. What the heck is that? Probably we don't have the right words for it, right? So that's fundamental, okay? And that's matter, right? But matter itself, what is matter? Matter is energy. That's E equals mc squared, okay? Wow, it's really cool stuff. So fundamental science, because that's it. Like you can break everything down to just building block ideas, okay? And by the way, all the ones I was talking about, mind-boggling ideas, those are the testable ones, okay? The newest ones like dark matter, dark energy, they're yet to be testable, or rather they are testable, but the tests aren't conclusive. So it's the most quantitative, okay? It's the closest to math. So physics plays an interesting role. Someone who likes math, I think of it as a good opportunity to practice math. I think of it as kind of a applied math class. You could have applied physics, which is kind of like their class is called applied physics. Colleges have them everywhere. But there's also applied math, which is kind of just physics. And so that's, it's a neat division. And so for those who really like math, fundamental math, and just thinking about math for math's sake, physics is, kind of a nice adjacency to that, right? A neat science, okay? So heavy use of mathematics, which makes the conceptual class, interesting, right? We could completely avoid it. We could just do no math at all, but I want to expose us to some of it. Not in the sense that I'm going to show us the giant, differential equations that require calculus, and big matrices or something, No, none of that. I'm just going to show us the accessible side of it and just talk about our ability to think quantitatively, because there actually is there's like a motivation to what it means to be a quantitative thinker and how we all have that in us because we all naturally want to ask questions. We all have a sense of inquiry, right? So that's kind of our window into mathematics potentially, right? Rather than it being kind of this useless tool that is just like, so frustrating because you can't learn it, right? So many of us have that experience, okay? So lots of numerical measurements. Everything is going to be measurable, right? We're not going to have cases where we're not going to quantify something and have some particular number associated with it, okay? Everything has units, all right? And, there's some ratios that don't, but they're all tied in with other things that do have units. We even have a fundamental, what are called the core units, the base units, that's not core, the base units of physics is just a few of them, really just a tiny handful. You might guess some, right? The equivalent of length, meter in the metric system, because the metric system is the system used for these base units. You got time in seconds, right? We all agree on that at least, right? Although seconds are kind of clunky with the 60 minutes in an hour. Just, mathematically, that's a pain in the butt, right? Whereas the metric system is all power is a 10, right? So time's always going to be a pain, okay? But then we also have, the other fundamental units, which are going to be mass, okay? And then interestingly, current. All right, because current charge is totally separate from mass. It's another fundamental property of particles. Neat, huh? All right, so there is minimal math, okay? Can't get around it. All right, so the first part of the physics that we're gonna look at is, as I said a while ago, is called classical physics, okay? That means that it comes from a point where, you have the classics in a sense, although it's more when Europeans in, certain parts of Europe in a period called the Renaissance, triggered by some economic phenomenon within northern Italy primarily, but a lot of other factors, and of course, subjugation of people around the world. It significantly started, and this was happening on the backs of their lives, right? So there's the whole interesting, very fascinating story of what humanity has done and benefited from, right? But that is what that's the period of history where classical physics started. So these were, again, Europeans in the 1500s. The period was where there was kind of a rediscovering of classics, which was the writings of Romans, right? So these Romans from like the 1st and 2nd century, which had been largely, not well known, but interestingly preserved over those many centuries, sometimes known as the Dark Ages, right? So then with the Renaissance, that's when people started reading these classics again. And that idea of the kind of digging back in after so many centuries and a kind of change in how people could spend their time then led to new ideas and a huge birth of new ideas. And that's where in that situation, in that kind of bubbling cultural new phenomenon, that's where particular individuals just were able to flourish. And they were going to be male individuals, they were going to be white because they had to have a certain amount of either usually just outright privilege. They were born into wealthy situations, almost without exception, but then some exceptions in terms of upward mobility because they'd be hired apprentices. Kepler is famous for that in astronomy. That's rare. So mostly these are people that were lords or had a huge amount of free time, and they were able to within this at least honestly in inquiry based trying to learn science for science sake, not to hurt people directly, but still these were people that benefited from their enormous amounts of money and the rest of what Europe was doing. I think you get the point, right? That the history is there, right? But then there's the discoveries, and so we had these just incredible amount of discoveries and just understanding of the world and understanding of things like conservation of energy and conservation of momentum and just making things work and then coming up with whole languages of quantifying it and filling up notebooks of equations and this was all new to humanity, right? This was just happening in the 16th century, 17th century. Okay, people have been using math, but not like you would see a problem set today or a math textbook with just like lines and lines of equations and so much notation based rather than full sentences. That was a whole new approach, and it just kind of bubbled up to the surface. But as often is the case, what motivates innovation? Well, war, right? And there was plenty of cases of of course this spreading subjugation of people that were able to be kind of taken advantage of, obviously, very much so from these white Europeans, but then just fighting over new resources in this age of colonialism, right? So you had a huge amount of advancement in terms of understanding fluid dynamics, projectiles, and so you had this early advance in that ideas, and we see that today. We have such big foundations in understanding projectiles, which probably indirectly but definitely led to that by the time when we started putting things up into orbit, we were able to do that so well, right? Because we understood projectiles and had for so many generations of people studying it for war. Okay, and right. But is it just about projectiles and shooting, lead balls? No. Or even shooting a satellite up into space fast enough that it falls around the Earth but never hits the ground, because that's what a satellite is. That's what orbit is. It's actually free fall the whole time. It's just moving so fast to the side that it never hits the ground. Well, I'll talk about that another time. But it's more than that, right? I mentioned light. Light is a whole amazing puzzle that's tied in. It kind of has facets into all these different branches of physics. And we can look at light that we see with the visible eye. That's that rainbow. That's the entire spectrum of light that that we're capable of based on these particular cells called the cones and the rods, and the cones are the ones that detect color, and that's just the range of wavelengths, because light is a wave, that the human can see. Well, that's a tiny portion of the overall electromagnetic spectrum, and so we can look in parts of the spectrum that would be invisible to the human eye using special goggles like infrared goggles. Here we're seeing what's associated with the heat signature, because infrared is actually a type of thermal radiation. It's a bunch of wiggling together molecules which are releasing photons in a continuous spectrum with a peak wavelength outside of the visible, and actually almost not enough intensity at all to us to pick it up, even on like the far red side, because by the way, that's the closest thing to infrared is red, right? That's the lowest energy, longest wavelength light that we can see. So here we have this weak light that we just can't pick up. It's just washed out by the light that we can see, okay? And we don't have the right cells for it. So, right? Put on the goggles, block out the light that we normally can see, all of a sudden we can see that heat signature. And it tells us different information, right? Because we can see here, heat escaping from this house around the doors and the windows, right? That's kind of interesting. We're actually seeing a story told by otherwise invisible light. And that's so important to so many branches of physics, is using that. It's one of our greatest kind of detection techniques, is using light outside of the visible spectrum. Pretty easy to build, circuits that can register it, right? So that kind of this, birth of electronics led to this ability to explore light more thoroughly. That's one branch of physics feeding into another. Okay, so in this case, right, we're seeing a mechanics approach, because we're seeing forces in motion at the microscopic scale. That's what things are wiggling around. They're actually moving. That's how you end up with these photons being released. There is motion. There's honest to God mechanics, right? But there's this happening with billions of atoms, right? That's actually how many atoms exist on a macroscopic scale of like a little block of wood that this house is made out of would be just actually trillions upon trillions. It'd be 10 to the 24, so a trillion atoms in one small amount. But that all that aside, once you zoom out, you've got that process, that movement of heat. That's called thermodynamics. All right. So if you imagine billions of little things all moving together, but no way to track every single one of them, that mass movement, that statistical movement, is actually a subfield of physics called thermodynamics, which is the study of heat, but also how that ties in with other physics questions like the classical questions and light. All right. All right. So here, someone's using a laser, by the way. All right. So we got electricity and magnetism. We've got optics, right? Because if you're going to take advantage of optics and actually build, goggles that can see infrared, you had to think of the circuit. Someone had to think of the circuit to do that in the first place, which means that you had fundamental people and like early scientists, not fundamental people, but early scientists that were doing experiments with these, we wouldn't think of them as circuits, right? But just these big contraptions that stored static electricity in light in jars, basically, built up some charge, and then they could release that charge and run it down a silver wire, right? So some wires, right, to do something else, right, to trigger something. And then they got the idea they could start building these circuits. And then one of the things these circuits can do is capture all kinds of different wavelengths, because you can have what's called this photoelectric effect. You can have photons, very selected for photons, depending on how the circuit's made, that then can trigger electrons, and those electrons then make your current, because that's when we talk about electric current, is in fact the flow of electrons, right? Okay, and not in terms of the individual electrons are moving slowly, but in their average movement. Again, story for another day, right? But point is, then that circuit, it allows us to detect optics. But that said, that would be for optics outside of the visible spectrum. If you just want to do plain old optics, people have been doing that well before they were able to build circuits or understand electricity. Scientists, these inquiry-based thinkers, they've been using lenses and curved mirrors to understand a lot about how light works. In terms of like geometric optics, like building, cameras, early cameras, all that sort of stuff's been happening for 300 years, right? 200 solid years of cameras, but more in terms of just like this understanding of optics, focusing light, right? Telescopes, microscopes, all of that. Okay, so all those fields, so mechanics, thermodynamics. Interesting, thermodynamics can kind of bleed over into modern physics depending on how you approach it, and it's kind of like a hot button topic. You can it's a field of physics that doesn't like to fit, but we don't need to focus on the problem child. We can lump it into classical physics. Is a good place to put it. That's where the first theories come from, historically speaking, right? So that's again mechanics, thermodynamics, electricity, magnetism, because again, this was all happening at this point. We're in the 18th century, 1700s, and then optics, right, which would continue throughout. So that's classical physics. Okay, modern physics starts with some key things that happen right kind of in the 1890s up through the 1920s in terms of understanding quantum mechanics, starting with some study of thermal radiation and this what's called Planck's constant, this idea that you can split up energy into little packets, which was not thought to be real, but turned out to be really fundamentally real, as far as we understand it, right? So quantum mechanics leading to nuclear mechanics, leading to the Bohr model of the atom, which kind of was birth of modern chemistry. All of that stuff, the building of the periodic table, right? All that, of course, that's chemistry, but that's coming in, from conjunctions, collaborations, I should say, between physicists and chemists, right? Or sometimes people don't call themselves one or the other, right? Some people don't consider themselves a physicist or a chemist, right? They're just a scientist that does, physics/chemical work, right? Often people, actually in the actively studying something, they wouldn't, identify with a clear delineation. Whereas when we teach the subjects, we write the textbooks, we split it up. Right. Then particle physics is, if you've heard about like particle colliders, like CERN in Switzerland / France, because it crosses both countries. It's a huge loop of a collider. There's a linear particle accelerator in Stanford. There are cyclotrons in the national laboratories in the Bay Area. Right. So those are all examples of the giant dramatic devices, these billion-dollar contraptions that basically create like racetracks for particles to ramp up to very high speed with giant magnets. Well, that's how particle physics are studied, because essentially particle physics is an amazing branch of physics that is really delving into the smallest building blocks that make up things like atoms that actually like quarks and so on, but other particles that just seem to kind of be rare but exist and kind of tied in with matter in all these weird, complicated ways. Because if you've heard of a quark, those are the building blocks of protons and neutrons, but it's not as simple as just saying, oh, there's 3 quarks per proton and 3 quarks per neutron, and they're different quarks. It's then sometimes quarks become bosons, sometimes, or maybe that's a category, but sometimes they might become a like a pi atom or something, or all these different types, which I can't remember the names of now. But point being is that it's this very strange and very, very kind of constantly evolving branch of physics at the very forefront of modern physics that is much more recent, by the way. It's not one that dates back to the turn of the 20th century. This is a branch of physics that really kind of started probably in the 60s, as far as I can think of, because if you have actual kind of new particles being discovered, neutrinos were one of the first kind of more exotic particles, and that would have come out of understanding nuclear processes. So some of those kind of first nuclear tests, so actually kind of probably the 40s then, right? Because we started understanding nuclear processes, seeing some exotic particles created, not even sure if they were real at first, would have started with those early nuclear tests. So then so from the 40s on was when particle physics was born, but it's come a long way. But it's still a very high energy phenomenon. It's not about maybe dropping nuclear bombs and looking at rare particles being created, but instead these colliders, they're all about crashing things together. The whole reason that they have these huge footprints physically, right? They're many miles across sometimes. Is that in the case of CERN, for example, is this giant loop right underground? Inside that giant loop you have often protons that are accelerated to incredibly high speed and then crash into each other. And that process, depending on how fast they're going, creates different particles, because different energies create different particles. That's one of the big breakaways from relativistic physics, right? This idea, which is not listed here, but it's tied in with all of them, right? And that can be attributed to Einstein, one of the greatest thinkers, But so relativistic physics would be kind of like have its thorns in atomic physics, nuclear physics, particle physics, condensed matter physics. You can't understand all of them, any of them, without understanding this idea that there's a continuum between mass and energy, right? E equals mc squared tells us, but we'll break that theory down when we get there. Okay, this is just all that. Hopefully, like big picture stuff that makes this topic interesting, right? And compelling, right? So here we have actually collecting energy from photons. Is that photoelectric effect? All right. So many applications of physics, right? The things that we didn't even think we could do. Think about the microcircuits that are every day. The breakthroughs to actually make those work, right? To understand how to just build these incredibly complex circuits on such a small scale. It's remarkable, right? And what we've been able to do with more satellites and better rockets, right? These reusable rockets. So I think there's really, really incredibly fascinating applications of this. And when you think about physics and what people do with it, interdisciplinary fields is one of the things that comes to mind, right? So applying physics to medicine, biophysics. My degree, actually, my PhD from UC Berkeley is in biophysics, so that's something near and dear to me. right? I wasn't on the medical side of it, by the way. I was in the more kind of like studying it on a kind of ecological scale, but not in an interest of conservation, but just kind of understanding like the physics of biological processes in terms of how things move throughout the environment. Whether those are tiny little particles that are called aerosols, or whether those are spores and this this process of spreading, right? How do those things actually happen, right? What are the underlying principles? And they're fascinating. How do they compare between water and air, right? And this is fun stuff to talk about. This is things that people think about when they think about the potential of life on other planets. How does the the nutrients necessary to life, how do they move from point A to point B? How do you end up with a process, a cell that is self-replicating, right? Because that's a physical process. That's an energy cycle. How did you get kickstart that energy cycle in the first place, right? How does physics explain life, right? Actually, and we don't know completely, right? There's unanswered questions, all right? So we have this application now, right? We can measure things, we can compare between theories, we can have one theory that is a little bit more accurate than the other, right? Knowing that, test them both and find out that within our limits of measurability, right, how our accuracy of measurements, both theories work. Well, take the easier one, right? That's often a takeaway, and I think that's an important one to kind of the everyday be realistic about, right? We have to use the language of mathematics, throughout physics, right? We can't get around it. We're not going to try to overwhelm ourselves with it, but we do need it, okay? And so you can look at that in terms of altering a recipe between different units. So if you can look, different section of the book. Let's flip over there real fast. Right. So we want everyday phenomena 1.2. Here we have, right? So this is showing a conversion. What's nice about this is the textbook really walks you through it, right? You have lots of explanation here, right? Thoroughly showing each step all the way through, right? So you can really come up with a nice result, and then try it with different numbers yourself, okay? Right, so here we see, an example, right, where we have recipes converting from one thing to another, right? So 10 servings, right, over 4 servings, so 10/4 of this, right? So if you want, right, so let's see, so we have a pancake recipe for 10 and a pancake recipe for 10, right? How do we do that, right? Because it's not double, right? So what's the ratio, right? Well, we had to multiply by 10/4, right? To go from 4 to 10, you have to multiply by 10/4. See? So you have to multiply each value by that 10/4. So if we want to convert the 1 cup, it becomes 2.5 because 10/4 times 1 is precisely 2.5. Let's try this one right here. Let's do, so the 3 eggs, right? Well, 10/4, right? 10/4 times 1 is still going to give you 2.5. But where did they get the 3 from? Well, they round up. Because you can't have half an egg realistically. So in a recipe, you'd round up. And you have to say, well, 0.5 is considered a rounding value to the higher integer, the higher next number, so hence rounding up to 3, right? On the case of 2, right? So here, let's take a look at that. If we just plug it in, right? So if I say I want to do my 10/4, because I'm going from 10 servings to, or rather going from 4 servings to 10 servings, and I know it's going to be 10/4 and not 4/10 because that 4/10 is a value that's smaller than 1, right? I wouldn't multiply by something that's smaller than 1 because that's going to reduce my recipe. I need to increase my recipe because I would need to serve 10 people instead of 4, right? So we've done 10/4 multiplied by 1, right? What about for something like the 2 tablespoons of sugar? How do we end up with a 5? Well, 10/4 times 2 is precisely the 5, right? So, and if one of these things, like let's say it said 3 tablespoons of oil, what would be 10/4 times 3, which would tell us that to serve 7.5, or to serve 10 people, so to have 10 servings, I don't know if each person is going to be exactly a serving, but to have 10 servings, we would then need to multiply any ingredient that has 3 for 4, right? We have to multiply that by 10/4 again, and our result would be 7.5. Right? So again, had this said 3 tablespoons of baking powder, then over here it would have said 7.5 for the larger serving. Okay? All right, cool. So that's kind of showing one of the things we can do with mathematics, right? One of the ways we can make a conversion, because we'll do that a lot. Right? We got to make a lot of conversions, right? Fundamentally. The other thing that we just can't get around, that we can't avoid mathematically, is this idea of powers of 10, which is part and parcel of scientific notation. Scientific notation, tied in with a metric system, all about powers of 10, right? But it's also just the way our numbers work, right? Because we've got 10, 100, right? 1,000, those are all powers of 10. So we start the next digit and then the power of 10, right? So when we talk about scientific notation, we talk about writing things not with a bunch of zeros, right? So which would be very cumbersome, right? So for example, written 1 trillion becomes 1 with 12 zeros after it, okay? Actually, it's 1 with 11 zeros after it. No, it is 12. Sorry, I said 11. 11 would actually be 100 billion, Okay, 11 zeros is 100 billion. 12 zeros is a trillion. Okay, how many is a billion? 9 zeros. Okay, and if you think maybe a million you're more familiar with, well, a million is 6 zeros. Okay, so that means that 1 million is 1 times 10 to the 6, or shown here, 1 trillion is 1 times 10 to the 12. Okay, so that's scientific notation. You have to put that in your calculator. It needs to be a scientific calculator because you can't, you can't do it on the most basic calculators. It's hard to find, the raising it to a different power. But if I go back over, I take a look, at which I put down here. Excuse me. And so if I want to do a scientific notation, if I say I have 4,567 times 81,782, right? So let's see. Oh yeah, it doesn't want the commas in there. All right. So I'm gonna see if this will give me scientific notation. See, it doesn't, right? It's kind of clunky, right? So here in Desmos, it's kind of hesitant to give you scientific notation. And in Write, that's the program I'm using, by the way. Great online calculator. You don't have to use the actual physical calculator in this class. It being an online class, if you're taking the class while you're watching this video, then just use Desmos, right? It's gonna work great. You can use it on your tests as well. Right? So you can see not written in scientific notation, right? If I wanted to write in scientific notation, it did clump it together in groups of 3. So I have 3 and 3, so that means that's a million. So what I have here then, just put in words, first of all, is 374, if I round, right, to the 1 million place, 374 million. Interesting, right? Well, that's the same as saying 3.74 times 10 to the how many, right? Well, 6 is a million, now we have 100 million, so 8. See? They match up. Now I rounded it, right? But look, it's the group of 3 zeros, right? For the, when rounding the way the 363, rounding the way the 530, right? Which is the 100,000s place. Those just become another group of zeros, right? So that's, now we're up to the 100,000 place on that 5th zero, rather the 6th zero, okay? And then, right, and then we get to all the millions, starting with the 4 million, the 70 million, the 7, right, and then finally the 3 for the 300 million. So we have 374 million, written in scientific notation as 3.74 times 10 to the 8, all right? And you get more practice of scientific notation by looking at Appendix B. It's a good place to look for it. Right, here's another conversion, dealing with the fact that, like I said, time is always a pain in the butt because it's not powers of 10, so you have to, when you do its conversions, you can't just do kind of simple, it's easy to convert from, say, like millimeters to meters, because a millimeter is a thousandth of a meter, especially once you get used to the prefixes like milli and kilo and micro, right? And we'll talk more about those, right? But point being is that you can't, there's no just simple powers of 10 of time, and you have to deal with those 60s. So you can see here that we have a 60. That's because we're converting from hours to seconds, so we're dividing by 60 squared. One thing I often do is I actually just divide by 3,600, because 60 times 60 is 3,600. So it's a real common conversion that you just have 60 times 60, 3,600, okay? And then you can also convert it into miles per hour, right? Because there's a conversion, not a precise one, because there's no precise correlation. It's just there's some agreement between the metric system and the American imperial system, is often called. And so so we say that a kilometer is 0.631 miles, right? But we could continue. There's more digits that we don't necessarily use. Okay. And I won't ask you to convert often between the systems. We're going to be basically sticking with the metric system, right? Some rare exceptions. All right, so understanding things like conservation of angular momentum, which is a really cool concept of rotational motion in general, but like stability on bicycles is kind of neat, and how that applies to atoms, and it turns out the quantified conservation of angular momentum, pretty cool concept, far out, but that's quantum mechanics. So this would be like an electron orbiting in the middle, an electron orbiting a proton, right? So again, a rotational system, right? Say a lot of the same physics, not precisely the same physics, but a lot of the same physics, right? And then that same principle then is going to apply to galactic motion, right? So hundreds of billions of stars all orbiting it together. That's what composes the galaxy, by the way. Even the Milky Way galaxy is about 100 billion stars. Can you believe that? Most of the stars have planets. All right. So trust me, physics is fun, right? You're gonna think about things differently. It's going to be a wonderful experience to exercise your mind. Okay. All right, well, come back to check out the second video. Basically all the other chapters, I'll split them into different pieces, but I hope you've got a fun introduction here and got a lay of the land, all right? So until next time, see ya.